Okay, so let us see a video of cone calorimeter ignition, how it occurs in one of the tests, where you have some salt water layer over which 1 centimeter oil is put and a heat flux of 5 kilowatt per meter square is given from the cone. You can see that I will play the video now. You can see that when the heating starts, you can see the vapors are coming out now, and there is a igniter, the spark ignition is also kept at a particular height, and you can see the vapors are coming out as the heat flux is radiant on the pool surface, and after a particular point you can see that the ignition occurs, and you can see the flame going over through the cone, and this flame will be the flue gases will go on to the chimney, and it can be analyzed. So, you can see this again, that first initially you can see it is a small flash occurred. Once the flash point is reached, then further heating is continued, then fire point occurs. There are 2 or 3 flashes you have seen now. Then after that fire point has reached, then a flame is established over. Now the ignition is not required. So, this is the way in the cone calorimeter we do the tests. So, different type of sampling can be done here. Okay. So, for example, the diameter, the radius or the diameter of the pool can be increased. You can also, so this is one of the trial, okay, second trial basically. So, you can do it for various heat flux, and the depth can also be varied, different types of fuels can be put, and so that is the advantage of this. So, now keeping this distance also you can vary, and keep the igniter, which is a spark somewhere from the normally we keep it from the surface 8 centimeter above it, the spark is kept basically to ignite it. So, when you see that 2 or 3 times the flashes are formed, then the ignition occurs basically in the gas phase and propagates to the liquid phase and sustains over the pool. So, this is one of the video where it is clearly demonstrated that how the ignition test is performed in a cone calorimeter. The second video what I am going to show is the flame spread. The flame actually spread. This is a dodecane pool of say about 1 meter long, and the flame is initiated here. It is natural convection, there is no flow, force flow. So, the flame is initiated in the right hand side and the flame spreads towards the left hand side. So, if you see carefully the features, when the flame spreads, you can see that here you can see there is a wave, surface wave which is propagating. So, from the ignition location there is a movement of the liquid layer, and you can see the surface slowly moves from the right to the left as the flame propagates, because here what happens is when the flame is initiated at the right edge, this is hotter, and you can see that the temperature decreases as we move from the ignition point towards the downstream where the unheated fuel is present, and this liquid is initially subatmospheric. It is at a low temperature than atmospheric temperature. So, you can see that there is a Marangoni convection which is caused due to the temperature gradient. So, here it is hotter. So, the surface tension will have a low value, and when the temperature decreases, the surface tension value increases. There is a flow at the surface which is triggered from the low surface tension point to the high surface tension point. If you see again that you can see the wave motion of this surface is clearly indicated by this dull light, the dull color which shows the movement. As the flame spreads, it actually moves the surface also. So, that is so this is in this way only the liquid phase convection will also be triggered. So, this is another example of flame spread for the sub flash condition. And one more thing we can what you can notice is the flame actually oscillates. It is not steadily spreading. So, it ignites, then it actually goes to some direction, then comes back, then goes. You can see the pulsation in the flame spread. It is not steadily spreading over this. So, these are the aspects basically which we have discussed, that when there is a liquid temperature which is lower than the ambient temperature or its flash point, we will have several phenomena like pulsation of the flame, triggering of a surface movement and so on. So, these are the important points. So, I will now go to the PowerPoint. We will continue from this slide, where we were discussing about the flame spread over methanol pool, which is actually at initial temperature varying from minus 20 degrees to 30 degrees. So, when the liquid is at very low temperature, we have uniform spread of low spread rate, and this is called pseudo uniform regime. When the temperature is increased in the range of the liquid temperature, initial liquid temperature is increased in the range of minus 10 to about say 3 or 4 degrees, then there is a variation, increase in the flame spread rate, but this is pulsating region. As we saw in the duodecane case, the flame actually comes forward, then goes back and comes forward, etc. So, this is the pulsating region. For different fuels, this temperature, initial fuel temperature range may be different for the pulsating region. For methanol, this is what it is, but for duodecane, it may be different. Then after it is heated up beyond say 2 degrees, etc., you will see that there is an increase, but now it is also uniform regime, flame regime. There is not much increase, and the pulsating is absent now. When you increase the temperature beyond the flashing point, you can see a good increase occurs in the flame spread velocity, and after that beyond 22-23 degrees, if you increase the initial liquid temperature, there is no big effect in the flame spread velocity. So, asymptotic region is reached. So, this is the aspect of flame spread, which is highly dependent on the initial liquid temperature. So, in this case, what happens when the liquid temperature is close to or above the flash point of the liquid fuel, when the temperature is there, initial temperature is like that, then you can see that a premixed type of flame spread occurs. That is, enough vapors are already available in the gas phase, which has mixed with the ambient air, and the flame has to just propagate over the premixed reactants. And since the liquid temperature is higher, enough vapors are already produced over the liquid surface, and the flame can just spread over that at a faster rate. But once the temperature is increased beyond a certain value, there is no effect of the liquid temperature on the flame spread rate. So, we have also seen this slide. The important aspect which I have shown in the video, when you have a liquid at sub-flash temperature, then the liquid surface does not remain stationary. We have seen the movement of the liquid layer. As indicated, when the flame heats up, there is a temperature gradient which is formed on the surface, due to which surface tension gradient also form. Because of that, the flame actually is going to push the surface from the hot point to the cold point. The surface has a movement. So, a recirculatory convection current is observed because of this. Okay, the temperature gradient, surface tension gradient cause the surface to move. A surface actually moves, and basically it completes the loop at a particular distance. We can say as the flame spreads, there is a certain distance between the edge of the flame and the surface movement. Okay. So, this is another important point which you should note, and flame spread depends upon initial temperature very importantly. So, to summarize, the flash point is very important because that will produce enough vapor, and if the initial temperature of the liquid is above the flash point, then the flame spread rate will be much faster. If it is below the flash point, several phenomena occur. The flame spread can be oscillatory, it can cause a surface convection, it can also have pseudo uniform regime, and so on. Now, let us see some aspects of parameters which will affect the flame spread, basically the pool depth and the pool width. Okay, now the pool depth plays an important role on flame spread rate. For example, if we take this, so this is the tray on which the pool is liquid fuel pool is kept, and there is a certain depth for it, say d, some depth. So when you have a certain depth, there is a certain heat transfer to the liquid phase. If you have very low depth, okay, then what happens is the flame need not propagate. So experiments have shown that based on the type of liquid fuel, again characteristics of liquid fuel like its volatility, flame will not spread over the surface if the depth is below a critical value. Example is for N decane pool, the depth is, if the depth is less than 2 mm, then the flame will not spread. Why? Because when there is a thin fuel layer, some vapors are formed due to heating, and the air from the atmosphere mixes and a mixture forms. But when this mixture forms, the volume of this mixture will be such that there is a heat release rate for this, but this heat release will be, so let us say Q dot, this will produce a Q dot, this Q dot will be less than Q loss. That means whatever flammable mixture is formed, that will produce some heat release, but this heat will be lost to the environment, so that this will not be able to heat up the layer and the flame will not spread. Okay. So when this is very small, that is what is happening, so that the flame spread is not going to exist. So the depth actually plays an important role in this. Critical depth is present for different fuels. For N-decane it may be around 2 mm, but for other fuels it may be different. Okay, now what happens? From a critical depth, I try to increase the depth of the pool. So what we see is the flame spread rate increases. So what I can say is the flame spread velocity and the depth of the, if you try to plot, that is a critical depth. So where you have a flame spread velocity, so below this there is 0. So that is a flame spread velocity for a critical depth. So this is depth critical. So I have value for the flame spread velocity like this. Now as the depth increases, the flame spread velocity increases, but asymptotically reaches a constant value. So after a particular depth, there is no effect of depth at all. The flame spread velocity will be the same. That means, as I told you, the liquid fuel evaporation is mass transfer dependent. So when the flame is formed, it is heating the fuel surface to fire point, which will produce enough vapor to sustain the flame, and the flame moves. So more heat is not required basically. So even if you increase the depth, the heat which is coming in from the gas phase to the interface and interface to the liquid phase basically is such that the temperature of the surface is close to the fire point, so that it produces enough vapor to feed the flame. Okay. So when the pool depth is increased beyond the critical value at which the flame starts to spread, it will asymptotically reach the maximum value, and after that the effect of depth, so I will say this asymptotic value of depth, after that it will not have any role. So now we talk about the width of the pool. So from top, if you see, this is the width from the top, if you see. So this is the length, and the depth is in the other direction, mutually perpendicular direction. So the fuel width also plays some notable role, not very significant role, but some role it is actually going to play. Why? Because if you see, when the flame spreads, when you see from this, the air entrainment can occur from the sides like this. So, if the width is very small, the air entrainment will occur and that will affect the flame spread rate, because when the width is say some small value, when you increase the width, then what happens is the air also entrains from this direction, the other direction also the air entrains. But when you increase the width to a particular value, then the air entrainment from the sides will not affect. So, after a particular value of the width, the effect of width becomes insignificant. Similarly, when the temperature of the liquid is more than the flash point, then also the effect of width will be insignificant. So, when you try to characterize the fuel, we want to know what is the flame spread rate. So, I construct a lab scale experimental setup in which I have a trough of certain length. Say I will have enough length, say maybe 1 meter or 1.5 meter length, so that I will have some good average value for the flame spread velocity. Similarly, a particular depth will be taken, which will be in this mode, like in this regime, where there will be no effect of depth at all. Similarly, I will take considerable amount of width, so that the air entrainment from the sides will not affect the flame spread rate. So, the effect of pool depth and pool width are very important for us to set up a experimental setup in which we will have good values, like the effect of other parameters can be easily judged. Now, how will you calculate flame spread rate? You can take good videos and understand. See, for example, I can have a pool, I can mark certain lengths, and I can find the time it takes for the flame spread over these markings. So, I know the distance between two markings, time taken for the flame spread over these two markings will give you the velocity, the distance by the time will give you the flame spread velocity. Or I can also calculate the area of fire. So, the flame spread rate is very important, because that will tell about the developing fire, how fast the fire is developing or growing, So, the growth rate of the fire can be established. So, for that what I do is, so let us take a circular pool, okay, and I ignite at the middle. A flame forms and it actually spreads like this. The flame actually spreads over this. So, we take maybe you require a larger pool and also a faster camera to capture this. So, the area of the fire, when you ignite at the center exactly, the area of the fire can be written in terms of, so this is radial direction. So, this is radius, and the radius of the flame varies as a function of time. So, the area of the fire can be written as, in terms of radius, as AF equal to pi r square, very simple, circle. So, it actually spreads as a circular flame from the starting as a point flame in the center and grows towards the edges. So, now area is known. What is the flame spread velocity Vf in meter per second? In meter per second, what is the flame spread velocity? It can be written as, so radius can be written as Vf into T, so that I can substitute this instead of radius here. So, AFT equal to pi into Vf into T square. Okay. Now, I can find the Vf basically based upon how the area changes. That is one aspect, but I am interested in another aspect, the growth rate of the fire now. Okay. Do you understand? So, how can I find the flame rate? I can have markings and the flame, how much time it takes to travel between these two markings. Please understand that the flame spread rate need not be uniform over the entire length of the pool. So, for example, it may be slower initially in these three markings and it may be faster in this, then again it will slow down. So, it is a non-uniform variation can be observed. Now, if you take, I I want to know the growth rate. For that, I consider a circular pool ignited at the center, and I write the area of the fire as a function of radius in terms of Vf into T, and substitute that. Now, what is heat release rate? Is nothing but the mass loss rate and the heat of combustion. Mass loss rate m dot will be equal to the mass loss rate per unit area into the area of the fire. So, this is kg per second, this will be kg per meter square second, and this will be meter square. So, get back. So, this is the mass loss rate m dot, and this is the heat of combustion. This is in kg per second, and this will be in kilojoules per kg. So, this will be in kilowatts. So, now when I write this, substitute for AFT pi Vf T square. So, I get m dot double dash mass loss rate I can measure. Putting this entire setup in a load cell, I can find the average mass loss rate. Then instead of AFT, I write as pi Vf square. T I have taken out, and delta Hc also included here. So, this which is there in this bracket, that I call as alpha, which is a factor that is dependent on the characteristics of the fuel. The fuel burns in a, of course, given the same ambient conditions, temperature, pressure, velocity, etc., the fuel has a given mass loss rate, it has a given flame spread rate, and delta Hc is the calorific value. Okay. So, now we can see that these are all dependent on the characteristics of the fuel type itself. So, we can say that the heat release rate is alpha times T square. So, when I say under T, I get a curve like this, alpha T square curve. So, this is the growth rate of the fire. So, starting from the flame spread rate, we can see that the flame spread rate basically can be written in terms of flame spread velocity, and we get a parameter grouping which is called alpha, which is the factor that affects the characteristics of the which is dictated by the characteristics of the fuel. Okay. Now, all these things in the alpha, m dot double dash, Vf, etc., can be got from flammability test, which we have seen earlier, and delta Hc can be calculated from the bomb calorimeter. So, that is the way you. So, the flame spread rate basically is useful in determining the fire growth rate, which is an important parameter for us. Okay. Ignition, flame spread, etc., depend on several factors, and once they are determined, we can use it for finding the fire growth rate also, and classify the hazardous aspect of the liquid fuel. Now, coming to the mass burning rate, when the fuel is completely spread over the pool, it burns over this, consuming the mass from the fuel. So, that is called mass burning rate. Now, all the transient things are normally over. The ignition, the subsequent ignition causing the flame spread, etc., are over. Now, a flame is established over the liquid surface, and it actually slowly heats up the liquid, and the mass transfer occurs. This vapor feeds the flame, the vapor feeds the flame, and basically this cycle continues until the entire liquid mass burns. So, when a flame spreads over liquid surface, it primarily heats up the liquid surface downstream and evaporates more vapor out of it and continues propagation. Okay, now propagation is over. When the flame propagates over the entire fuel surface, now again thickness comes into play, correct. So, when you have a thin fuel surface, what happens is basically the regression see the liquid when it is consumed at one point, the surface again becomes planar. That means this surface regresses. I will talk about it later in the next slide. The surface will descend down as the fuel is consumed, correct. So, that means that when this propagates itself, the liquid can be consumed in the flame. That means there is no, the flame need not be established over the entire surface, as the when the thickness is too small, the flame, or maybe it is just above the critical thickness of the fuel pool, then the flame as it propagates also can consume the fuel, and when it finishes propagating, fuel also will be over, complete, like it will not be available for further burning. So, that is what the thickness aspect is. But if it is thicker enough, then the flame would have spread over the surface, but enough fuel is again present underneath the flame, where it will continue to evaporate and feed the flame, and the heat feedback will couple with the mass transfer now. Okay, now, so we have a finite thickness of the liquid layer. Then what happens is, after spreading, the flame starts consuming the fuel below it. So, for say thicker fuel, we can say the rate at which fuel is consumed becomes almost steady. So, we take a thicker fuel and there is a flame which is fully established over this surface. Then what happens is, slowly the surface regresses, slowly and steadily, not only slowly but steadily. That means, the mass which is coming out is at a given rate. That is a time dependent phenomena. When you see the height, the surface slowly goes down, but if you see, the density of this will be of order of 1000 density of liquid, but density of vapor is of order of 1. So, we can see that it needs the lot of mass is there in the liquid phase. So, slowly it has to evaporate and come out and burn in the gas phase. So, that is why when the flame is established over this, if there is no change in the flame anchoring positions and the standoffs, then the burning will be almost steady, and also the surface reaches a temperature which is constant, called equilibrium temperature. We have already seen that. So, now this combustion is fuel vapor comes from the surface by diffusion or aided by convection. Similarly, ambient air comes from the surroundings to the flame. So, this combustion process, when the entire pool is surrounded by a flame, is controlled by convection and diffusion, or we can say transport processes. Transport process control that. Do you understand? So, this is true for both fuel which is transferred from the surface to the flame, or for the oxygen which is transferred from the ambient air to the flame surface. And of course, the heat transfer from the flame to the surface is important for aiding the continuous vaporization of the liquid. So, the mass burning rate is one in which you have some certain quantity of fuel which is left over after the flame has spread over the entire pool, and the flame has formed over the entire pool surface, and now it starts consuming the liquid below it at a rate which is almost steady, almost same rate it evaporates, and this burns. So, this is the characteristics. So, what are the factors which is going to affect them? We will see. Whenever we have seen that evaporation occurs, there is a concentration of the fuel at the interface. So, I say YFI, and at far off distance it is YF infinity. So, the gradient of this, so this is actually non-linear variation you will have. We have already seen that it is actually some exponential variation. So, exponentially the interface mass fraction decreases to a, and asymptotic reaches the value of the fuel mass fraction at the far field. So, the gradient of the fuel concentration or mass fraction at the interface drives the mass loss rate. We have already seen that due to Fick's law. So, rho F, Vf equal to rho v yf plus rho df a dyf by dx minus. So, this is the fixed law, and we will see that this is the predominant factor affecting the gradient at the surface. This is actually surface, that is what is affecting. Do you understand? Basically, when you remove the vapors at a faster rate, then this gradient increases, more evaporation occurs. So, in the convective condition, it may be laminar or turbulent condition, as the fuel vapor from the surface is removed at a faster rate towards the flame, the mass burning rate increases. So, if you do not have any convection, the mass burning rate is low, and when convective field comes, the mass burning rate increases. So, in the normal gravity conditions, buoyancy driven flow will influence the burning rate, obviously any convection basically. So, now let us talk about the regression rate. As I told you, the surface, when the burning occurs, the surface actually regresses at a particular rate. So, we can say the regression rate of the surface R dot, which is actually meter per second or centimeter per second or meter mm per second or anything like that. It is like a velocity term. The rate at which the surface regresses R dot, okay, that can be associated or expressed in terms of the mass loss rate kg per second as the area of the pool A into the regression rate R dot into the liquid density. This is liquid density. Okay. So, you can see this is kg per second, this is meter square, this is meter per second, this is kg per meter cube. So, meter cube and meter cube cancels, and this is kg per second. So, this is the relationship between the mass burning rate and the regression rate. Okay. And you can see that there is a descent in the layer, but this descent happens at a steady state. So, for example, in a given time, see, let us say the depth is about say 10 mm. In about 1 minute, it descends 1 mm. After 2 minutes, it descends 2 mm. Then it is a steady regression. Do you understand? So, that is what is called steady mass burning rate.